Welcome guys, I'm Sandip from askIITians. Today we are going to start our previous chapter, that is force and pressure, right? So this is our third session. In the previous two sessions we already learned what is force. Force is what? We can say push or pull, right? Then we also have studied the different types of forces. Four fundamental forces are there, right? I hope you remember those. Then we know that contact and non-contact forces are there. Then we also know what is friction, normal. Then other tension is there, right? We already studied a lot of about those, right? So today, in the same chapter, we are going to start a new topic which is called as pressure. Okay, so let's start. Okay, so now about the force and pressure. First of all, pressure means, what is pressure, right? Normally, when we say pressure, it most probably we say that it is related to liquid, right? Remember, the pressure chapter mostly relates to the liquid, we can say, but even solids, we can also say solids also have the pressures, right? So very simple definition we can do, right? For the pressure, it is the force per unit area, right? What I can say, pressure is nothing but force per unit area, right? So as I said, it is mostly related to our liquids, right? So today we are going to start our lecture by watching very interesting movie, right? Which I know you already know about that. It is the Titanic, right? Obviously, we are not going to watch the movie, but short video how the Titanic actually sank into the ocean, we can say, right? So let's start with this one and watch very carefully what are the different things they are showing you.
Pretty good.
Right, so
Around the iceberg, try to keep from.
See, this was the animation that did how the Titanic must have hit the iceberg. Okay? What I want you guys to observe here is that iceberg. Watch very carefully that iceberg thingy. And obviously, the main question arises that the ship is very, very big and how it could even float on the water. Not the Titanic, even the small ships also, how they could even float on the water. And so I hopefully you will be you will have the clear idea after this session that how the sink or ships will float, right? And I also want you to research on that. Just spend some time, right? If you do have the curiosity, right? Today I'm going to explain why it is floating. I'm going to explain just the concept, right? Archimedes concept is there, Archimedes principle is there, binding forces are there. I'm going to provide you some concepts, but I'm not going to tell you exactly how it is floating on the water. That's up to you now. I want you to search something on that, and in next session, hopefully, you will be aware that how the ships are floating, right? So in this video, again, first of all, let's see how the ship is floating, and again, I want you to clearly observe that iceberg.
Hitting the propellers, that looked pretty good.
Here, can you see that iceberg above the ground and below the ground? Right. This is also the very important concept in our chapter, right? Or we can say in pressure or fluids, right? Can you see the part which is above the ground? The below the ground part is very, very bigger than the above the ground. So anyway, we know that Titanic was very big, right? Iceberg that must have hit the Titanic should have been the way bigger than that one, right? So can you imagine how much part which is inside the water of that iceberg is very, very big, right? Okay. So this is the important concept. When we see the ice floating, the most of that part of that ice is below the water. Okay.
Okay.
And that is also the important property of, we can say, any object which is flowing into the water. Okay. So this is how Titanic sank. And as I said, there are many questions. The first question starts with how actually it floats. It's a very big, right? Then second question, I said that iceberg, the most of the part of that iceberg is below the water. Why is it like that? We will also understand that. And I definitely asked you one question. I want you guys to research on that, how that ship is floating. Obviously, I'm going to teach you the concept today. You should be able to apply that concept on why this ship is actually floating. Okay, good. So now back to our chapter as force and pressure. Force, we have already studied a lot of things, and now about the pressure, what things we are going to cover today is the pressure. What is pressure? Then what is the atmospheric pressure? Then obviously pressure in liquid we can say, and Archimedes principle, very important, right? Buoyant force is there, upthrust is there. All those things are making possible that big ship or any big ship rolling on the water. Okay. So first of all, when we say pressure, I told you pressure is what? Pressure is nothing but force upon area, force per unit area. Simple. So now consider if there is one plane like this, and if I apply one force here, this force which is perpendicular means we say it is a normal means 90 degree. This force is called as thrust, right? And as I said, that force applies we can say its effect is applied on whole that area. We can see here, this is area, right? Consider this area is it could be pi r square. If it is circular, rectangular, then you can calculate it L bar L into breadth, right? Same thing. But just it is a area. If some force applied normal to that area, then the pressure is developed in that area. That is given by force upon area, right? Simple. Can anyone tell me what will be the unit of pressure? Obviously, we know the formula force upon area. We know the forces unit is what? Newton, right? What is the unit of area? Meter square. Okay. So you can say the SI unit, this is called as the SI unit. The SI unit of pressure is Newton per meter square. So this is the SI means this is the unit universally, which is universally accepted. So you can go everywhere and tell that is the Newton per meter square is the pressure. That's everybody will say it's okay, right? And it is also called as Pascal. So instead of saying Newton per meter square, now we are going to say it is a Pascal. Why? Obviously, Pascal is the name of scientist, right? We already know Newton force has the unit Newton because of that Newton scientist. Similarly, Pascal studied something on this fluid and pressures and etc. etc. Therefore, unit for the pressure is Pascal. Okay, this is not the only unit. There are other units for the pressure. One bar is also another unit. Let's say this is what 10 raised to 5 Pascal. This is the conversion between 1 bar and Pascal, we can say. There is another one unit that is 1 atmospheric pressure. Again, this is 1.013 into 10 raised to 5 Pascal. Sometimes pressure is also measured, right? In terms of height of the mercury, right? So remember, this is called as mercury barometer. Contains just a simple setup there, container which contains this mercury, right? Everybody here must have heard mercury, hopefully, right? So what we do, we take that instrument everywhere. First of all, consider sea level. We say sea level. Now let's see what is sea level. We know this is ocean. We already seen that in Titanic, right? Consider this is the mountain. Okay. If you take this instrument here, what will happen? Here you can see I have shown that mercury is rising like this up to certain height. Okay. So this height is actually going to tell us what is the pressure at that particular point. If I take this whole instrument, let's say at the sea level, that mercury is going to rise up to height of 76 centimeter, right? Therefore, I can also say that this is also called as 1 atmospheric pressure. We will see what is 1 atmospheric. ATM means atmospheric. So this is known as atmospheric pressure. We already know 1 atmospheric pressure is 1 into 1.013 into 10 raised to 5 Pascal, right? Okay. So now I also can say this is nothing but 76 centimeter of Hg. Hg means mercury. So pressure is also measured like that. Now consider if this same instrument, if you take this instrument on the, let's say, top, what will happen? This pressure is going to decrease. Let's say 70 centimeter now, right? So what I can say, at the top of the mountain, the pressure becomes 70 centimeter of Hg. This is how I can measure the pressure using this instrument. So it could be 76 centimeter of Hg or 760 millimeter of Hg or 0.76 meter of Hg. Hg means again mercury, right? So those are the different, we can say different units of the pressure. Okay. Now, again, from this formula of the pressure, that is pressure is equal to force upon area, right? So this is my formula. And force is, I have given the another name for the force, that is thrust, right? So can I say P is directly proportional to thrust and P is inversely proportional to area? Meaning is very simple. What I can say here, if the force increases, pressure increases. If the area increases, what will happen? As I can see, it is indirectly proportional. So if the area increases, pressure will decrease. Remember, if the force increases, pressure also increases. If area increases, pressure decreases. Right? So we can take a very simple example. We know the hammer and nail, right? If consider this is the wall and I want to put a nail into the wall, obviously you will apply some force due to this hammer, I can say, right, on this nail, right? Simple. Now, as you can see, at this point, area is larger. Let me call this as area. And at the tip of this nail, area is smaller. So can I say A1 is greater than A2? What about pressure? It is inversely proportional. So obviously, pressure at point 2 will be greater than pressure at point 1. So very simple thing I can see here. Whatever force you are applying on this area A1, it will exert more force at the tip, and therefore it is going into the wall, we can say. Right? So this is what happens actually here. Okay. So this about the force and area and pressure. These are the different relationships. Remember, if the area is larger, pressure will be smaller. Right? If area is smaller, pressure will be larger. Okay. Now let's talk about the pressure in the fluids. So consider this is the water tank, or just consider, let's consider this is our big container. We have the big container of water here. And what we are going to do here, consider this is the imaginary cylinder. What I'm talking, it is the imaginary cylinder which is immersed in that, or we can say this is the imaginary cylinder of water, we can say. So this is, everywhere there is water, there is no cylinder, but consider there is a imaginary cylinder now. Now let's point out how many forces are acting on that. Can I say that water is acting the force on that any object? We already have seen in that our video that everywhere water was applying some pressure, right? So can I say this is the pressure everywhere, here also, here also, right? Similarly, this will be the pressure upward, this will be the pressure downward. Let me call this as P1, let me call this as P2. P2 is at height, let's say H2. P1 is at height H1. So obviously, difference between these two will become H2 minus H1. I will call it as H. Okay. Now, about the horizontal forces or pressure, we can say. Can you say that that all will get cancelled? We already seen those things in the force concept, right? If we applied the forces on the opposite side, what will happen? They will cancel each other, right? It will be like a null effect. Okay. So obviously, we don't have to worry about this blue forces. Just consider about the P1 and P2 forces. And now I want to prepare the formula for pressure. Okay. So what we can see, if this is the cylinder and that cylinder is now at equilibrium. If you do remember, when we say the cylinder is or any object is in equilibrium, when all the forces acting on them are similar. Horizontally, now we are not considering, we know that they are cancelling each other, but not P1 and P2. P1 and P2 will have the different quantities or different values, I can say, because as the depth increases, right? As the depth increases, what is going to happen? Pressure also increases. Right? Remember this part very carefully. As the depth increases, pressure is also going to increase, and we want to calculate that pressure. Obviously, at this particular point, at H1 height, it is P1. At H2 height, it is P2. Can I say P2 is greater than P1? That's right. So let's say P2 minus P1 is it our final pressure or net pressure, we can say. So instead of pressures, we know in terms of equilibrium, when we get the equilibrium, when there is a forces are equalized, we can say. Now there are these two forces. Rather, I can say force because of P1 is what? I have the formula for pressure. Pressure is force upon area. Using this formula, can I write F is equal to pressure into area? That's right. Pressure into area. Now come here. So using that same concept, I can say P1 is equal to what? F1 into A. P2 is equal to what? F2 into A. Simple. Okay. There is another one more pressure on that, one more force on that cylinder. I haven't shown that. Anybody can recall that, right? Yes. Think on that. Which force should be there? One more important, very important force is there. Right? That's right. That is mg force. Mg is always acting towards downward, right? So now we are going to equate all these forces. We already seen equate vertically upward forces to vertically downward forces. So let's equate P1 is F1A, P2 is F2A, right? So sorry, there is a mistake I done here. This is upon A and upon A. Let me see at the top we have what we have written. Yeah, force is equal to PA, right? So instead of that, let me change this one. I can say F1 is equal to P1A and F2 is equal to P2A. Right. Now at equilibrium condition, what we are going to do? Vertically upward forces should be equal to vertically downward forces. We are not talking about the horizontal forces. Why? Because they are cancelling each other out. So let's see who are the upward forces. Only P2 I can see is the upward force. Downward is which one? P1 plus mg. Can I say this is P2 minus P1 is equal to mg? That's right. Okay. Now, before moving ahead, I want you to know one more important quantity here, right? So, quantity is called as density. So we'll study a little bit about this one, which will be useful in our this small derivation, we can say. So density is equal to mass upon volume, right? Density is equal to mass upon volume. SI unit, I can say this is nothing but kg per meter cube. Why? Because masses unit we know kg and the volumes unit is meter cube. So this is our simple formula for density, right? So one more thing, if the density is less, or just consider this point. If this is the water, consider one iron sphere. If I took one iron piece and drop here, right, what will happen? It will go to the end of the bottom of the tank, right? What will happen if I put the ice in that? Will it look something like this? Right? Iceberg we have already seen. So we know ice is floating, right? Ice is floating and this iron is sinking, we can say, like Titanic ship, right? Okay. So why this ice is floating and iron is sinking? There are three things we are supposed to know here, right? One is water. There is water, obviously. Then iron and ice, right? So all this sinking or floating, these conditions are dependent on buoyant force, we know that, and as well as density, right? So there are two things. So this is the density. So let me mark the density of all these three guys, right? So density of, let's say, water is, remember this value is very important for us, 1000 kg per meter cube, or we can even say 1 gram per centimeter cube. Similarly, density for, let's say, iron is given as 786 kg per meter cube, or I can say it's 786. No, I think we gotta check the ion's density. It will be a lot more than this. Just give me a minute so I can just check the density of iron. Yes, it is 7864 or 74, we can say this much. Or in gram per centimeter, I can say this is 7.8 gram per centimeter cube. And we also have the ice, right? For ice, I can say it is almost 916 kg per meter cube, or we can even consider 900, right? Or let's say this is 0.9 gram per centimeter cube, right? 0.916 or approximately, let's take approximation it, let's say 0.900 kg per meter cube. Okay. Now, using these relations, can you tell me why iron is sinking and ice is floating on the water? Obviously, you can see density of water is greater than density of ice, therefore ice is floating. Density of iron is greater than density of water, or I can say density of water is less than density of iron, right? Therefore iron is sinking there. Very simple thing, right? One more thing, this is the 900, right? So 900, and now let's focus on water and ice only, right? Before that, let me write one more concept here, that is relative density. Now what is relative density? It is the ratio of density of substance upon density of water. Normally we do say density of different substance, but here we can consider the water also, right? Specific gravity, there is another term actually for when the second part is water, it is called as specific gravity, but in general term now we can just consider relative density is equal to density of substance upon density of water. So if I want to calculate, let's say relative density of ice, relative density of, let's say, ice, I want to calculate, what I will do, what is the ice's density? Approximately we have taken it 900. What is the density of water? 1000. Can I say this is 9.10, right? Okay. So remember, there is one more very important formula, that is a fraction of, let's say in this case ice, we can use any substances actually, but we are talking about the ice now. Let's say fraction of ice which is, or let's say submerged underwater, submerged in water. What is the meaning of that, right? So consider if this is the ice is like this, we have seen this in the video also, right? Submerged means this part, right? So fraction of ice is submerged in the water is the relative density, which is for ice we got 9/10. 9/10 means 9 of the 10 part of this ice. So if this is the, let's say 10 meter, then 9 meter, or let's say 10 kilometer, will be 9 kilometer will be below the water, we can say 1 kilometer will be the above, right? This depends on the relative density. We also have seen that in the video, right? I told you to watch it very carefully, that iceberg which has a very big part of it inside the water, right? Who decides that? This relative density is going to decide that how much will be the part which will be inside the water. Okay. So now we talked about the density. Now let's come back to our small derivation. Density, we know the formula, that is mass into volume. So can I say from this part that mass is equal to rho into volume? That's right. So let's substitute it here. Rho into V into G. Rho into V into G. Now, sorry, again, I think I did the mistake again here. It's F2, this should be F1. right? Forces we are talking about, no? Not pressures. Yes. Now let's substitute the values here. F2 means what? P2A minus P1A. Okay. Or can I say P2 minus P1 is equal to rho into V into G upon this area. Area can be taken as common and let's take to the RHS side. Now, when we say volume, rho into volume, let's talk now. This is our cylinder, right? This cylinder we have considered. What is the volume of cylinder? Can I say it is area into this height? Right. So if this is the area, this is height. So can I say H is V by A? That's right. So I will get the answer. This as rho into G into H. And this is, let's call this as pressure. P is equal to P2 minus P1. That is pressure difference, we can say. So the pressure difference between these 2 points will be how much? Rho into G into H. This is our basic formula. Okay. So this is how we can find out the formula for pressure. Then, now, why I said that P2 minus P1 is rho GH. Now, just assume that this cylinder starts from, I will draw another diagram here. Yes. So now consider, this is the water, right? Cylinder starts from here. So obviously at the top, how much will be the pressure? Here it has some pressure, that is H1 we have said here, right? Here at the top, still have some pressure, which is called as atmospheric pressure. Atmospheric pressure means everywhere we have some pressure because of, we can say, gaseous material which is present in our atmosphere, right? Right? Which gases are present in our atmosphere? Anybody? That's right. Nitrogen is there, oxygen is there, carbon dioxide is very, very less than that, and others are in very, very small amounts, right? So all these gases also creates the pressure at every point in our room also, right? So it's not like that only water has the pressure, air also has some pressure. That pressure is called as 1 atm. We already seen that at the sea level, right? We talked this one. At the sea level, the pressure is 1 atmospheric pressure. As we move upward, what happens? Pressure decreases, right? Remember that part. Okay, so this is atmospheric pressure, and obviously compared to water's pressure, we can say it is not very high, right? So can I say that pressure directly at this point is equal to rho GH? Right? So instead of saying P2 minus P1 is rho GH, let's say P is equal to rho GH at this particular point, we can say. We can also consider one example here. Remember, dam. Dam means the other dams which are stopping the waters, right? In rainy season, we store the water, and in summer, we use that stored water for our this water comes from dam to our home, we can say. Now, you can see these are the dams. This is the wall of the dam. It is not like this. It is like that. It is getting broader and broader at the bottom. Why it is happening like that? As I said, as this height increases, or we can say depth increases, pressure of the water increases. So obviously, at this particular point, pressure will be very high compared to this point. Therefore, wall needed to be bigger at that part, or broader, we can say. Right? So remember this part also. Why dam has the bigger or broader walls at the bottom than at the top, we can say. Right? Okay. So this is the basic formula we have seen about the pressure, and we also know about the density now, right? Okay. Now let's talk about the Pascal's law. Now, what is Pascal's law? We already said that Pascal studied all this fluid mechanics and pressures, etc., etc. Therefore, what we can see, our SI unit is a Pascal. Now let's see what actually the Pascal said. Pascal said that consider this is the closed container. Consider this is the closed container, and obviously some water or any liquid is in there, in that container. Now consider if there is a small opening here and we apply some pressure from this side. Let's apply this pressure, right? Normally what we will say, this pressure applied will be for this point, water at this point or this point or this point. But what Pascal did say, that whatever pressure you are applying, pressure, how you can apply the pressure? By the force, right? You use some force on that and obviously pressure will get applied. Pascal said at every point, the same pressure will be applied, right? This is the basic principle of Pascal, we can say. And very important, you will think that is not very important, but remember, this has many applications in our daily life even also, we can say, right? So let's see what Pascal said. So according to Pascal's law, any force applied to the confined fluid, confined means enclosed fluid, is transmitted uniformly in all directions throughout the fluid, regardless of the shape of container, right? So here you can see some different shape of container is there, and if you apply the pressure on one side, second side will also get the same pressure. So what is the use of that? Now this part is this diagram which here you can see is called as hydraulic lift. Hydraulic lift. You must have seen this in let's say garage, right? Car garages. There will be some, even in the two-wheelers case also we can say there are some hydraulic lifts are used which are very small actually, right? For two-wheelers, yeah, we can say. Now consider if you want to lift the car, how you can lift it? We cannot directly apply the force to lift, or it's not like that four people are going to come and they will lift the car and then the mechanic will repair that car, right? That's not going to happen. So what they do in this case, or how the Pascal's law is very important, as I was saying, it's like that. So consider, this is our hydraulic lift, as I was saying. So this is a small piston which we can even operate on by our hand, right? Here it is a very big area, you can say base area, which is more than size of the car, obviously, because we want to lift the car, right? Okay. So now consider if the car is kept here, something like this, and we want to lift this car. So what we are doing, this is the very small piston, you can say, with the small area A1. So area, can I say area is less than A2? That's right. Okay. So when we are applying this, pushing this piston, this is called as piston, right? If we push this piston downward, what will happen? Some pressure will be generated here. Let me call this as P1. P1 is also equal to F1 upon A1, I can say. So pressure is developed at this particular point. And what Pascal said? Pascal said same pressure is developed at every point in this container. So everywhere the same force is going, same pressure is going to develop, not force, but pressure. So this force applied is very small, right? Pressure generated, area is also small. Pressure generated is transmitted everywhere. So if I consider this is the P2, and I say P2 is F2 upon A2, means force on the area A2. Now A2 area is very big compared to our A1 area, but which quantity is similar? P1. So can I say P1 is equal to P2, or F1 upon A1 is equal to F2 upon A2, right? Simple. So tell me, if now consider if this small pistons area is, let's say, 10 unit, right? If I applied the force of 15 unit, A2, as it is very large, let's say it is 1000 unit, right? And this area, sorry, this area is 1000, yes. And we want to calculate the force F2 with which that piston is going to move upward, with which that piston is pushing that car up, we can say. So we want to calculate F2. Simple calculation is there, right? So can I say F2 is equal to 1500 Newton? Let's call this as Newton. Let's say this is meter square. Meter square will be very high, I guess. Just say it is 10 unit and this 1000 unit. So what I can see here, if I apply the 10 Newton, 15 Newton force, obviously I'm getting a very large force which can be used to lift the car. Obviously it will be, car will need the greater force of, than this. Car's weight is how much? Maybe 500 kg or 700 kg something. So it will need 7,000, 8,000 Newton force, right? So obviously we also have to increase the area. Let's say area is 10,000, you can say you can lift up to 15,000 Newton, right? So it depends on the areas. You can increase the forces quantity if you increase the area there. It's very important thing we can say, that is Pascal's law. Okay, this law is also used in your brakes of the bike, we can say. Normally in most probably in sports bike, if you have seen somewhere at the handle, there is some very small, like this small ocean which contains some oil type liquid, right? In that, right on the handle I'm saying, right? If you have the sports bike, watch on that handle, there is a small, you can say, compartment which contains the oil. Now this oil is actually went through like this, right? And we can say this is your, let's say, tire of the two-wheeler. It is connected like this. So this oil is flowing through here like this. And now consider, if you want to apply the brake, what you are going to do? You are going to exert some small force here. Also, this area is also small. Here, when it went to the tire, this area is larger. So A2 will be larger. So F2 generator will be larger, right? So with that force, this is a rubber type material which we can say brake, right? And it goes towards the tire, we can say like this. And now it is going to stop the tire. So this is called as hydraulic brakes. Hydraulic brakes. In trains, these brakes are very important. They use these brakes in hydraulic brake. These are very sensitive, very urgent brake, we can say, right? So this is also another application of Pascal's law. Okay. Now let's move to our next concept, which is called as buoyancy, right? Or upthrust, we can say. So what is buoyancy? Buoyant force, it could be, we can call it as buoyant force, buoyancy, upthrust. All these things are what? It is upward. It is an upward force exerted by liquid. What we can see here? It is the upward force exerted by whom? Liquid or fluid. Fluid means, what is the difference between fluid and liquid? Fluid means anything that could flow. Even gases are also fluid. Air is also fluid. And liquid means we already know, or water, oil, etc. are liquids, right? So buoyancy or buoyant force or upthrust means what? It is the upward force exerted by whom? Liquid or fluid, which opposes the weight of immersed object, we can say. Object could be fully immersed, or object could be partially immersed, right? So this is called as buoyant force, we can say. Now this upthrust, how to give this upthrust? We already seen the formula for the pressure which liquid applies on this object. Even in this diagram you can see, right? Liquid is applying some force on this block, we can say, right? Or we can I say pressure is being applied by the water on that block. So upthrust means force. Remember, this formula for the force is pressure into area, right? Very simple. Pressure is what we have said. Pressure is nothing but rho into G into H, right? Into area, right? Again, tell me, what is area into height? Area into height is nothing but volume. So can I say this upthrust or buoyant force is also called as buoyant force? Buoyant force. Right? Formula becomes very easy. That is rho into V into T. Now what are these rho? Rho is the density of liquid. Normally we do have the examples of water. So we can say it is the density of liquid. G is acceleration due to gravity, that we know. Now this volume is very important part. Right? What is volume? Is it water's volume? No. Is it block's volume? That block is inside that liquid? No, it is not a block's volume. So what volume is it is? Remember, this is the volume of displaced water. Right? So again, the new concept is there, that is the displaced water. Now let's see what is displaced water. Right? Now consider here in this diagram they are shown. I have redraw this diagram. Consider this diagram has some water like this. What will happen if I insert, let's say, this wood they are saying, right? So if I put some wood into that wooden block, obviously this height is going to increase, right? So of the water is going to increase like this. Simple, very simple to understand. And this, whatever volume of that water is increased, I'm not saying height, whatever volume of that water is increased, which is called as displaced water. Okay. So is it same to the volume of displaced water or not? This is the our important concept, right? And obviously which will tell you how the ships are floating and how it is happening actually, right? Before that, obviously we will need some concepts why the or we can say principle of flotation, how it will float, right? So first of all, let's talk about that. So this is the buoyant force. Just remember this part right now. Then we are going to see the Archimedes principle. Right. So what he says, Archimedes says, when any object is immersed in a water, like this, we have immersed the cube, wooden cube there, right? It experiences the buoyant force that we also know, right? And that buoyant force is equal to, remember he said, buoyant force is equal to weight of the liquid displaced. Who displaced the water? That cube. The whole part is displacing the water? No, it is not. We can see the wooden, some part is also floating above the water, we can say, right? So only the weight which we can say that liquid has displaced, right? So there is one experiment he did actually. Now consider there is one, let's say, small block which has, let's say, weight is equal to 5 kg. Now if you tied a string to this block and let's say you immerse this block into the water, and now if you weigh this one using the balance, or let's say consider this is the spring balance upward like this, it will show you the 5 kg. This is 0 1 2 3 4, right? So pointer is showing 5. Now what happens if this is immersed in the water? You will see its weight is going to decrease. It will be, let's say, 3, right? So here the weight becomes 3 kg. Why this is happening, right? This is called as actual weight. First one is called as actual weight. This is called as apparent weight. Right? So he gave another statement there, that apparent weight, he said, Archimedes said, apparent weight is equal to actual weight. It is decreasing, right? So there should be minus sign, and he said it is subtraction buoyant force. This is what he said, right? So actual weight means we can say mg. Sorry, apparent weight, I can call this as mg dash. Actual weight, we know the formula, right? Mg weight is given by mg, and this formula we have written, that is rho vg, right? So he gave us another formula. Okay, so apparent weight is equal to actual weight minus buoyant force. Then now first of all, let's see what are the principles or conditions for the flotation. Then we can see whether it is sinking or floating, right? As we already seen that density decides whether it should float or sink. We have seen the iron at the start of the lecture, that iron is sinking, right? And what happens to ice? It is floating. What about the wood? It is also floating. How much it should float above the water surface? That also we know. It depends on the relative density of that material, whether it is wood or whether it is ice. It depends on relative density, we can say. So if the density is small, it will float. If the density is large, it will sink. Right? We have already seen the relative density here. Right. So relative density, or also I say specific gravity. Normally we use the specific gravity word when the second medium is obviously water. Right? So relative density is what? This is the ratio of density of substance to the density of water. We can say reference material is water. Right? So if the relative density is less than 1, we can say it is less dense, right? Like this. So ice is less dense than water. Okay. Then let's see, yeah. Then we already talked about this, right? This is the dam, we can say. As the pressure is increasing, it will be higher at this point and lower at the top. Therefore, we have the walls of the dam like that. Okay. So now, as I was talking, let's talk about the principle of flotations, or the conditions for flotations. Right now, we already know what is relative density and why it is floating, right? But still, my question is there, that why that ship, which is as bigger as Titanic or any other ship, obviously it will have a lot and lot of density. Why it is floating? Okay? So first of all, let's see what are the conditions. So flotation, simple concept I can write here is weight of the floating body, could be ice or anything. Weight of the floating body is equal to weight of the fluid displaced. Water displaced, we said it right earlier. Fluid displaced. There are three conditions I can give. That is, let's say work, sorry, not work. Weight of body is greater than, let's say, buoyant force. In that case, I can say, as we have seen in the case of iron, right? It is going to sink like this. The second case, if the weight is equal to buoyant force, remember, the body will float like this, but it is completely submerged. This is called as submerged under the water. It is floating, but it is under water. Right? And if third condition is, if weight is less than buoyant force, it will float, but some part of that body is going to above the water surface. Right? So remember this three conditions. Now let's see why our ship is sinking, or I will tell you, as I said, I will just tell you the concept. You have to find out why the ship is floating, not sinking, why the ship is floating. Okay. So as we said, weight is equal to buoyant force, then it is going to float, right? And also, this buoyant force is dependent on rho into V into G, right? This is what we have seen. V is what? Volume of that, volume of the displaced water, we can say. Now consider this volume or displaced water. Now consider this is the container. Okay? And let's say I immerse the solid sphere here. Right? It is completely solid inside. Right? So you will see that the sphere has the volume 4 by 3 pi r cube, right? If it is like that, it is floating like this, obviously we can say that water displaced in this case, we write it here. This is the volume of sphere. So water displaced will also be same, right? Water displaced is, again I can say 4 by 3 pi r cube. Right? Okay. Now consider second case. This sphere is hollow, right? What I'm saying, this sphere is hollow with this very small radius, or can we say inner radius is r1, or let's say capital radius is r. Okay, inner radius is small r, capital radius is r. So how much is the volume of that sphere? Is it again 4 by 3 pi r cube? No. Okay. See, it will be 4 by 3 pi r cube minus 4 by 3 pi small r cube. Why? Because there is nothing inside that, right? What is inside that portion or sphere? Nothing. That is air, right? So volume of sphere is only this much. And tell me, what will be the volume of water displaced? This is volume. Volume of water displaced is how much? Is it this one? Same volume? No. How much is it for me? 4 by 3 pi r cube. Right, now you can see the difference very clearly here. Even though the solid that metal was sphere, it is displacing the same water. Still now it is hollow, but now it is not displacing the, it is still displacing the same water. Here it is inside it, that part will be just air. So what you can see here, we have used the smaller volume. The volume of the second sphere is smaller, but still the water displaced will be higher. Right? So if the water displaced is higher, buoyant force will be higher. Right? If the buoyant force increases, right? If the buoyant force increases, then what will happen? That we can say this water is going to push this upward. Right? So what we have to do now, again you can see here weight of this part will be mg, or can I say this is rho Vg? Let me call this as weight W1. Right? W1 means mg, that is the weight of that whole sphere. This is the W2, let's say, or rho Vg. Yeah. Let me call this as W2. And I again say mg, but the volume is different, smaller volume, right? So again, the formula is rho Vg. Let me write this as sphere. This is also sphere. This density is also of sphere. Again, this density is also of sphere, right? And what about the water displaced, weight of the water displaced, or buoyant force, I can say? In this case, rho Vg. This is of water. Rho is of water. Volume is also of water. Again, I can say buoyant force is also here rho Vg. Rho of water, V of water, and G, right? Okay. Tell me, in both the cases, what happens to the buoyant force? Is it changing? No. Why? Because the water displaced is same. So buoyant force is remaining same. What about the weight? In the first case, weight is, here you can see volume, as we can say volume is greater in the first case. So let me write this as V1 is greater than V2. Can I say W1 is greater than W2? Or in the second case, buoyant force is remaining same, but the W2 is getting smaller, right? So weight is getting smaller, buoyant force is getting, or we can say weight is getting smaller, buoyant force is remaining same. So if the weight is small, what happens? It floats, right? Simple. In the first case, water, if the water is greater than buoyant force, right? Consider, just take one example. If weight is, let's say, 100 and the buoyant force, using all these calculations, right? Just take the arbitrary values. Consider weight is 100 Newton and the buoyant force is, let's say, 80 Newton. What will happen? It will be the first case, right? So it will see. Now what we are going to do, we are decreasing this weight. How we are decreasing this weight? Instead of having that full solid sphere, we have decreased this weight by introducing the cavity inside. Right now, consider this W2 is becoming, say, 50 Newton. Buoyant force is still same because it is anyway displacing the same volume, right? So buoyant force is again 80 Newton. So for the same case, right, we just created the cavity in that object. Now what we can see, we will get the third condition here. Now the weight is becoming less than the buoyant force, therefore it is going to float. Very simple thing. So now, as I said, use this principle and find out why the ships are floating, right? Okay, sure. So these are all the concepts from chapter. Now let's see some questions there. Very simple questions are there. Right? So liquid pressure depends upon what? Liquid pressure means what? We have studied this one. Pressure is equal to rho gh, right? Rho is constant, g is constant, so it depends on height. Very simple. So remember, this is a frequently asked question. Liquid pressure depends on what? Rho gh, that is height, you can say. Then hydraulic lifts, hydraulic brakes. We have seen both the things, right? Hydraulic lift is used to lift the car. Hydraulic brakes are to apply the brakes, right? And we know those are very sensitive brakes and emergency brake, we can say, which are mostly used in trains. These are used in what? Archimedes principle? No. Stokes, we don't know. We haven't seen the Stokes here. Bernoulli's, we don't know the Bernoulli's. So only two options are Pascal and Archimedes. Which one it should be? Archimedes is related to something buoyant force. Hydraulic brake, hydraulic lifts are related to Pascal's law, right? Now let's consider the third one. Pressure due to water will be greater at of the dam. We are talking about a dam, right? I have also told you this concept. What happens at the top, pressure is less. At the bottom, pressure will be high because depth is high, or we can say height is very large at that time, right? So can I say it is bottom of the dam? That's right. Very simple. Now, relative density of mercury. Right. If you do remember, I have given you the three different densities, right? So they're talking about the density. Let's do one thing. Relative is not the word here. It should not be. Let's talk about the density of the mercury. So we already seen that density of ice. This is the density of ice, right? This is the density of water. This is 786, which should be 4 something, 7864. This is for iron. So remaining is the density of the mercury. So you should know all these densities of mercury, let's say ice, iron, and water, right? So remember, mercury and water are the very important things in 11, 12, JEE, JEE, everywhere you are going to require this mercury's density. So mercury, we also have seen that pressure, we can measure the pressure using the mercury barometer, right? So this mercury is very important in this pressure or fluid mechanics. And water, as obviously water, we are going to study a lot about the water. So these two densities are very important. That is, water is 1000 and mercury is 13600. Okay. Good. So now, this is the whole of the chapter. We also have today we have learned about pressures and why the ships are floating. Still, you are supposed to study about that. Do some research on that. Why the ships are floating, right? Obviously, there must be some architecture in that, or design. We can say design in the ship that buoyant force should be greater than weight. There, weight could be whatever, right? We have seen in the Titanic ship there are a lot of levels, we can say, right? So weight could be whatever, but the only concept is buy and force should be greater than that. And why, how that buy and force is greater, that you have to search on. Okay. Then we also have seen up thrust, then the bind force, then the pressure, density, relative density, how much part of any substance is above the water, all those things, right? So here we have completed all our the first chapter, we can say force and pressure, right? So very simple and remember very important chapter, right? According to our physics, which we are going to require for even for 9, 10, as well as 11, 12, G, CT, NEET, etc. Okay. So do one thing, study this chapter very carefully, and if you do have any doubt, please put that down in your forum so I can solve your queries there. Right? Okay. So in next chapter, in next session, we are going to start about the friction. Like second chapter is their friction, and again we already studied something about the friction, but we'll study that in detail now. So we'll meet in the next session. In meantime, try to solve the questions on this chapter. Also, I've asked you one very important question, that why ships are floating, what are the design of the ship. Look into that, and if you do have any queries, put it in the forum. Okay. Sure. So thank you very much. We'll stop here. Have a nice day.